Yes, so this is work that I've been doing mostly with my former postdoc boss, Frédéric Monnier, who's now at IPGP in the University of Paris. But this is stuff that we've been doing more recently in my work, research here in the University of St Andrews and our isotope labs. Before I start, I'd just like to thank Sohan and the rest of the NorCell crew for putting this together and for inviting me. It's been a really fascinating few days, so I really appreciate it. I should also say that a lot of this research we've been doing for a couple of years now, and the first paper from it on the kind of source of zinc, terrestrial zinc, which I'll touch on a little bit in this talk, was just published in Icarus. The supernova stuff, hopefully we're writing up and we'll submit relatively soon. So the idea, what we want to think about, what I'm thinking about really here is how we go from a giant molecular cloud to a compositionally heterogeneous solar system with rocky bodies on the inside and volatile material, more volatile rich material on the outer part of the solar system. And of course, we have a point here in our solar system, n equals 1, where life is supported. And what sort of conditions led to the amount of this sort of specific amount of material and composition of material that led to the composition of our Earth, which somehow led to the evolution of life. And the tools I use for this are some of the tools I use are so-called mass-independent isotope anomalies in primitive meteorites. So I'll go through, so those are a lot of long words, so I'll go through each of those in turn. The main thing that I want to highlight is that this word mass independent, in terms of what I'm looking at, is isotopic variations which cannot be related to the terrestrial isotope budget. So these are, in the case of what I'm looking at, nucleosynthetic anomalies, which implies a chemically heterogeneous solar system. So the feedstock for the different planetary bodies in the solar system, there was either a sort of unmixing of material, or there was no full homogenization of material at the start of the solar system in the pre-solar disk. So as I said, what I'm looking at are nucleosynthetic in origin. There are some exceptions, such as oxygen. It's a famous one, but this is some points towards some incomplete homogenization of the solar system. And as I said, I use these tools to, first of all, these can point to different or various nucleosynthetic sources, so stellar sources into the giant molecular cloud of material that collapsed to form our solar system. The second is, because these are not process related, they are source related, we can also look at variations across material in the solar system to look at different sources where we might be sourcing material when we're accreting the planets. Are we limited to radial distances when we're accreting, or is there movement of material, large scale redistribution of material across the solar disk? And also, again, one other thing is, of course, to fingerprint meteorites, and also genetic relationships between perhaps primitive meteorites and differentiated bodies such as planets and larger asteroids. Now, I talk here about primitive meteorites. These are my main tools, and the reason is because if we think about, and here's a classic cartoon, which every time you go into Google and type in planetary differentiation, this is the first thing that comes up. Whoever made this, the whole of geoscience thanks you. So this is the classic idea of accretion of a rocky body from dust and gas, which gets large enough to melt, to get hot and melt, to differentiate. Now, the primitive meteorites, so-called chondrites, these are derived from material from bodies that are kind of on this side of this cartoon, bodies that never really got large enough to differentiate, so to separate into a silicate mantle and a metallic crust. So these are basically, if we're to take this as our model, these are essentially a composition of one of these that we can hold in our hand is the same composition, or relatively, you can link this as this composition of this larger asteroid material. And so that's why chondritic meteorites are so powerful, is that they've been unprocessed by differentiation processes. And just like in any science, and there's not going to be a test, so this is just to show you that there's a large array of chondritic meteorites, and these have been sort of split up on the basis of their mineralogy and their chemistry, and also their isotope chemistry. But what I want to point out is that there are three main classes, that is the carbonaceous, the enstatite, and the ordinary. And there are some other smaller subclass, sort of other classes down here. But the main observation is that carbonaceous chondrites are typically much more volatile rich, and they've tend to have undergone variable amounts of aqueous alteration, these carbonaceous chondrites. They've also got quite a lot of organic reduced carbon in as well. And the idea, based on this and other isotopic constraints as well, is that, so here, I'm just going to show you some nice images, just to show you the variability of the sort of chondrite meteorites. These are stunning rocks, they're absolutely beautiful. They're even more stunning under the microscope as well. And these small rounded grains here, these are the so-called chondrules, hence that's why they're called chondrites. Anyway, this idea that carbonaceous chondrites, these are kind of wetter and they've undergone aqueous alteration on their parent body, this broad view that the carbonaceous chondrites come from material that's further out beyond the snow line, beyond sort of around where Jupiter's orbit is, or beyond there. This is from material that accreted there, whereas the enstatite and the ordinary chondrites are from material that accreted, these are from bodies that accreted in the inner part of the solar system. So drier, hotter, more reduced. So this is one thing I want you to hold on to: the carbonaceous chondrites out of the solar system, enstatite, ordinary chondrites in the solar system. And these are what we can analyze to sort of see if this sort of dichotomy, or see if there's any radial distances, because again we've got this radial distance from the sun defined by these enstatite, ordinary, and carbonaceous chondrites. Do we see variations in isotopes in terms of their mass-independent anomalies? So that's when we get to what I'm going to talk about, the isotopes of these so-called iron peak elements. These are these elements around iron. These are generally formed in the cores of massive stars, either through explosive nucleosynthesis or via the S process. In a why addition is that these have got high binding energies per nucleon. So their nuclear structure is relatively very stable compared to elements on the other side. So when you form them, when you slam neutrons into something else to form a new element, that element doesn't want to decay. It's happy being where it is. So essentially you can build up high concentrations of the iron peak elements and also the idea of nuclear cross-section as well. They're easy to smash stuff into as well. So these are the iron peak elements, and what I was getting to is that within the iron peak elements and other S process nuclides, there are anomalies in the solar system that separate the enstatite and ordinary chondrites, which are in red here. This is from a review paper by Toss and Kleiner, which was released a couple of years ago. So this is isotope anomalies in titanium, chromium, oxygen, molybdenum, ruthenium, and nickel. These are complicated figures, but the main thing to point out is that 0 on all of these figures is at the Earth, right? So anything that's different from 0 on these figures is something that is made from a reservoir of material that is not Earth-like, right? So you can see that there's a lot of variation away from 0. That's the main thing I want you to take from this. And the other thing I want you to take from this is that there's a seeming gap in isotope space in all of these plots between carbonaceous chondrites and associated meteorites, which are the outer solar system material, and enstatite ordinary chondrites, Mars and the Earth and Moon, which fall in this inner solar system sort of drier plot here. So red is inner solar system, blue is outer solar system. And the idea is that this is sort of basically, the idea is that this is, well, one of the prevailing views is that this is showing that there's 2 reservoirs in the solar system. And there is not a huge amount of exchange, material exchange, at some point that things start to creep together. And one culprit that stopped material exchange is the formation of Jupiter. So if Jupiter formed, then it would form a kind of, essentially a barrier between material exchange from the outer solar system and the inner solar system. So that's the kind of prevailing view. Again, here's just some more. So this is another, these are iron peak elements: chromium, nickel, titanium, calcium. 0 is the Earth. You can see there's variation away from that. Carbonaceous chondrites are up here in the positive quadrant, and in both of these things, in both of these plots. So the summary for this introduction is that this solar system shows this radial isotopic heterogeneity. So you're seeing different parts of the solar system accreted from different sort of feedstock, which is obvious, maybe, but at least this is proof of it. But the Earth seems to plot on a mixing array often between inner solar system materials and outer solar system materials. What I want to point out, which is quite important, is that N-site chondrites, this group of meteorites, tends to always plot the closest to Earth. So that's an important thing to hold on to. The N-site chondrites always tend to be the closest isotopically to Earth's composition. So it seems that the Earth plots on this mixing array in many systems that suggests that the Earth actually could be a combination of inner solar system material dominated by inner solar system material because it's close to N-site chondrite, but with perhaps like a sprinkling of carbon outer solar system material coming in there. But most accretion models, if we try and put the Earth together from our known meteorite population in terms of chemical composition, they suggest that the Earth accretes most from N-type chondrite, so inner solar system, dry, hot-like material. So, where does zinc come in? Well, zinc is the most volatile of the iron peak elements. And of course, talking about life, I thought I should put in something about life. Zinc is, of course, crucial as an active center of some enzymes, and it stabilizes certain protein structures, like a lot of the transition metals in biology. But to date, zinc is the only iron peak element system, isotope system, where no bulk meteorite variations have been measured in solar system material. There have been in these odd phases, such as called refractory phases, called CAIs, just to say that they have been measured in the 1990s. There was one study where they measured relatively small. Again, this is on epsilon units. Again, here 0. These are the isotopes of zinc, I should say, 64, 66, 67, 68, and 70. This is 0, and there are some anomalies in 66 here and 70, perhaps. But none so far have been discovered in bulk meteorites. The prevailing view is that because zinc is volatile, that perhaps these, because in terms of its condensation sequence, is that most anomalies, zinc was still a gas when a lot of this heterogeneity was being controlled, was being defined, and so it was well mixed before any of the zinc condensed, or a lot of the zinc condensed, right? So a lot of people sort of suggested, well, the reason you can't measure them is that the solar system was homogenized for zinc, but not for these other more refractory isotope systems, which condense out of the solar gas much more early in the condensation sequence. But they should be there to some degree, right? Because they're measurable in some meteorite phases. So we went back and we tried to measure them, and to cut a long story short, we can measure them. They are there. So this is the first time that zinc isotopes have been found to be different in terms of their isotope anomalies to Earth in primitive meteorites. And this is a summary of the data. And so I'll talk you through these two plots. Again, 0 is Earth. This is the magnitude of the anomaly, the isotope anomaly on the y-axis, and on the x-axis is just the mass of the isotope. So this is zinc 64, 66, 67, 68, and 70. What you've got to do to look for isotope anomalies is you've got to get rid of that stable isotope fractionation, so you normalize to a fixed ratio. And that's why here x is 68 to 64, and that's why 68 and 64 are at 0. Because we basically reduce these to 0, and we see if there's any extant, there's any sort of deviation from 0. So we normalize to get rid of natural stable isotope fractionation, which is always going to be there to some degree. So this is just normalized to the pair of isotopes 68, 64. This is normalized 67, 64. And I'll mostly concentrate on 67, 64 because I believe, and we believe, that the anomalies are actually, the anomalous isotopes here are 66 and 68. And so what I want to point out is that carbonaceous chondrites have anomalies in 66 and 68 when normalized to this ratio here. Positive anomalies, and the inner solar system material, ordinary and enstatite, have kind of complementary negative isotope anomalies. So, and these are distinct at the 95% level, just to say that's and what we're showing here is the group averages. So we didn't just, this is just not one point, I should say. This is our group averages. Here are the data split up. Again, you can just, if you want, you can just look at this plot here. This is just the 68 and 66 anomalies plotted and correlated for the different meteorites that we analysed. And again, I'll point out that we have our carbonaceous chondrites here in the positive quadrant. We have Earth, these are terrestrial samples in orange here, and we have our inner solar system, enstatite, and ordinary chondrites down here in the negative quadrant. EL6, we won't talk about that. They're weird. Well, we can talk about it later if you want, but this is an interesting sort of meteorite that's very volatile depleted through kinetic processes, through collisional processes. Here is those data correlated with other iron peak elements. So chromium, calcium, titanium, nickel. These are the most neutron-rich of all of these isotope systems. And you can see again, we've got relatively good positive correlations where, again, we've got the positive outer solar system material, negative inner solar system material. Okay, so I want to quickly talk about what this means for Earth's building blocks, first of all. So where did Earth get it, because it plots between inner and outer solar system material, where did Earth get its zinc? And as a corollary, you could say, where did Earth get its other moderately volatile elements that are lithophile as well, right? So I won't go through this, but essentially what you can do, you can take a lot of, you can take all of these anomalies and you can play a game of saying, what mixture of meteorites from our known reservoir meteorites can we put together to make this zero, right? So here's a bunch of anomalies. This is from Dofar, 2014. These are a bunch of isotopes, again, zero Earth. Enstatite chondrites are in green, you can see closest to Earth. And this is just taking a bunch of these different meteorite groups, adding them together in various proportions and seeing if we can minimize this to zero, right? So what is Earth made out of? So that's what we've done with zinc. Remember though, of course, that most models, most successful models have a high proportion of enstatite chondrites in the successful modeling because they are so close. However, for zinc, Earth is not like enstatite chondrites. We can't make Earth's, we can't take all of Earth's zinc from the inner solar system. So what we did was just put together a Monte Carlo simulation, and what we varied was to look at different, because it's a large parameter space, this is the problem, right? So you've got to have some way of exploring this large parameter space to see if there's any patterns in there. And so we put together some mixing models based on Monte Carlo methods and we varied the amount of carbonaceous chondrites, so that's outer solar system material, enstatite / ordinary chondrite, inner solar system material. But what I also did was allow another parameter that we allowed to vary was the concentration of zinc in these meteorites as well. So this is just the outputs, and then we looked at what this predicted would be the zinc isotope anomaly. And every zinc isotope anomaly, that's the successful ones that are zero, are highlighted in red here. So then we picked these out and we plot them up again, and these are the successful mixtures which end up with an Earth that has no isotope anomaly. And so this basically shows that these successful models, again, this is the problem with Monte Carlo models, is that almost you can get any answer you want, but there is some pattern in the data. The first is that there's a wide range potential of carbonaceous chondrite fraction accreted to Earth. So let me explain this bottom panel more. So this shows the successful results of these successful models. This is the amount of Earth by mass that comes from outer solar system material, and this is the concentration of zinc in that material. In blue, it's the carbonaceous chondrites, the outer solar system material, and this is the inner solar system material. What I hope you can see is that all of the inner solar system material has to be relatively low concentration of zinc. This is always lower than that, right? This is outer solar system material in blue, this is inner solar system material in green. So this is depleted in volatile elements, which we know, which we could predict it anyway, but it's good that it's coming out of the model. And again, we've got a wide array of the amount of carbonaceous chondrite material, but based on other isotope systematics, we know that this can't really be more than 5%. What's great is the average is about 5%. So this is just these data plotted as a probability density. So this is the fraction of Earth from carbonaceous chondrite based on our models. And this is the amount of Earth zinc that this will have brought. So this is saying that based on these successful models, we brought around a third of Earth's zinc budget, total zinc budget, from outer solar system materials, even though this only represents about 5% of the mass of Earth. So the outer solar system had to be relatively wet, and it brought this amount of material with it. Now, this is telling us a few things. First of all, it's telling us that you can, even though there is a barrier there, apparently in the isotope space, that we think might be Jupiter, there is possibility of bringing material from the outer solar system into the inner solar system when we're accreting material that is volatile enriched. Okay, and I think that's one of the major observations. So that's the findings for this. So the zinc isotope anomalies insist on an outer solar system volatile element component, and the inner solar system had to be, the accreted form had to have been volatile pure. I think I've run out of time, so I'll just say that we think that based on mixing models that we can also use these zinc isotope arrays to look at what material is causing this isotope anomaly. So what is this isotope? What forms this isotopically anomalous material? So we can use the fact that we've got paired anomalies and use a number of stellar reaction rate models to see which, if we sprinkled a little bit of this material into the solar system, what could we generate this slope in our paired isotope array. And this is what this slope is here. And here's a bunch of different nucleosynthetic models from across the literature. These are large core collapse supernova, type 1 supernova, it's the S process models up here. But the one that best matches are these low mass core collapse or electron capture supernova, which best match the material that's causing these anomalies. So that suggests, we think, that it's a small mass core collapse supernova. And this agrees with nickel isotopes as well. I'll show you this. But what's great is that what I would point out is that this is where this electron capture models come from. This Wenadjo paper. If you look at their zinc profile here for what they predicted, it looks almost exactly the same as what we get for our. If you brought this back to 0, if you normalize to 64 and 67, you'd get a peak in 66, 68, and 70, and that's exactly what we see up here. So that's but again, hopefully you see that the power that isotopes can tell us about how planetary systems can form. Okay, thank you.